Have you ever dropped a ball and predicted exactly where it would land, but then watched a leaf fall and realized you could never predict that path perfectly? Why does one follow order and the other, chaos? That question takes us to the heart of today's topic, classical mechanics and chaos theory, the bridge between predictability and unpredictability in our universe. Welcome to the Learning Studio, and in today's episode from our physics playlist, we'll explore how the laws of motion laid down centuries ago still guide modern technology, from robotics and autonomous systems to AI-based predictive models. You can watch the entire physics playlist by clicking the link below in the description. This topic is part of our section Classical to Modern Transition, Control, Fields and Motion, and it's one of the most fascinating journeys you'll ever take in physics. The Clockwork Universe, Birth of Classical Mechanics. In the 17th century, Isaac Newton transformed our understanding of motion and force. His three laws of motion and the law of universal gravitation gave birth to classical mechanics, the science of predicting how objects move. For centuries, scientists viewed the universe as a perfect machine, like a cosmic clock. If you knew every position and velocity of every particle, you could, in theory, predict the future completely. Planets, pendulums, projectiles, all followed elegant, mathematical paths. This was the age of determinism, where nature's behavior was seen as predictable, exact, and absolute. But as science progressed, something strange began to emerge. Even systems that followed Newton's laws exactly could behave in ways that seemed completely unpredictable. This was the beginning of chaos theory. When predictability breaks, the birth of chaos. In the 1960s, meteorologist Edward Lorenz ran computer models to predict weather patterns. He made a tiny rounding error, changing one number from 0.506127 to 0.506. The result? The model produced an entirely different weather pattern. This small change in starting conditions caused massive differences in outcomes, a phenomenon Lorenz called sensitive dependence on initial conditions. It gave birth to the now famous metaphor, the butterfly effect. A butterfly flapping its wings in Brazil could set off a tornado in Texas, not because it literally does, but because nature amplifies small changes into big effects. Chaos isn't randomness, it's deterministic unpredictability. It means that even though the laws are exact, the results can be impossible to forecast beyond a certain point. Mathematics of chaos, order in disorder. Chaos theory revealed that nonlinear systems where small changes in one variable cause big changes in another, can produce patterns that are both complex and deeply structured. From weather systems and fluid motion to heartbeats and population growth, chaotic systems follow intricate paths that never repeat but still form recognizable patterns called strange attractors. Mathematically, this connects to fractals, infinitely complex shapes that repeat at every scale. It's the same geometry found in snowflakes, coastlines, lightning bolts, and even your lungs. Nature, it turns out, is not just linear and smooth, it's nonlinear, sensitive, and astonishingly intricate. From Newton to AI, classical mechanics in modern times. Even in our digital age, classical mechanics remains the foundation of engineering and technology. It governs how robots move, how cars accelerate, and how satellites orbit Earth. But now, combined with chaos theory and artificial intelligence, it's helping us model systems that were once too unpredictable to understand. AI-powered simulations use chaos-based models to predict weather and climate patterns, optimize robotic motion and drone stability, model financial systems, and even improve neural networks, because chaotic systems can mimic the adaptability and creativity of the human brain. In short, chaos isn't the enemy of prediction, it's a deeper form of it. The harmony between order and uncertainty. Classical mechanics gave us the rules of the cosmic dance. Chaos theory showed us that even when the rules are clear, the dance can still surprise us. Together, they reveal a universe that's both structured and alive, one where even the smallest motion can ripple into infinite complexity. This is the Learning Studio, and this was our episode on classical mechanics and chaos theory. If you enjoyed uncovering how order and unpredictability shape the universe, from the swing of a pendulum to the algorithms that guide AI, make sure to subscribe, like, and check out the physics playlist linked below. In our next episode, we'll journey into the invisible structure of reality itself, quantum field theory and unification, where particles become vibrations in an infinite sea of energy. Because in physics, even chaos follows a pattern, if you learn to see it.